All right, strap in, everyone, because today we are going deep. You sent us this excerpt from Alan Turing's 1936 paper on computable numbers with an application to the Entscheidungsproblem. And wow,
It's a big one.
yeah, this paper is, well, it's basically legendary.
Yeah, I mean, talk about a landmark paper. It really is like the big bang of, computer science.
Exactly. So Turing basically lays the foundation for everything we do with computers today.
Yeah.
And he did it all before computers even existed.
I know. It's like he was writing from the future or something.
Yeah, it's wild. And what's so interesting to me is, Turing wasn't just trying to invent a new gadget. He was wrestling with these deep questions about math and logic.
Yeah.
Like, what are the limits of what we can calculate and what can be proven and what's just, like, unprovable?
Yeah, some really big philosophical questions. Definitely not your average beach read.
Right.
So our mission today is to try to unpack Turing's ideas and explain them in a way that hopefully makes you feel like you've, time traveled back to witness this scientific revolution firsthand. It was a revolution, for sure. It totally changed the way we think about information and how to solve problems.
Okay, so let's start with the basics. What are computable numbers? I mean, the term itself just sounds kind of intimidating.
Yeah, it does sound a little scary. But basically, imagine a simple machine that can follow instructions. You could write down a set of steps, a recipe, if you will, that this machine could follow to spit out the decimal representation of a number. Well, then that number is computable.
So it's not about the specific machine, it's about whether or not there is a process, like a recipe, that could, in theory, produce that number.
You got it. And this is where Turing's genius comes in. He wasn't focused on building an actual physical machine. He was more interested in creating this theoretical framework, a way to understand what's fundamentally calculable, regardless of the actual nuts and bolts technology.
Right, and to do this, he invented this thing called the Turing Machine. Okay, I remember hearing about this in school, but I'll be honest, it always seemed very abstract to me. Can you break it down for us? What is a Turing machine?
All right. Picture a long tape, like a roll of film, divided into these squares.
Okay, sure.
Each square can hold a symbol, like a 0 or a 1, and the machine has a little head that moves back and forth along the tape, reading and writing symbols, and it follows a set of rules. Really simple rules like if you see a 0, change it to a 1 and move to the next square. Or if you see a 1, move back 2 squares.
Oh, okay. So it's like a simplified version of how our brains kind of do calculations, breaking things down into these tiny little steps.
Yeah, exactly. And the crazy thing is, this really simple model, this machine with a tape and a few rules, can actually capture any computational process.
Wow, really?
Yeah, it's a way to represent anything that involves manipulating symbols according to a set of instructions.
I've never thought about it that way before. So this basic Turing machine can, like, handle any type of calculation.
Well, not just any calculation, but it can handle a surprisingly wide range of them. Turing showed that. Even really complex numbers like pi or e or the roots of algebraic equations, these are all computable because there is a finite process to calculate them.
That's amazing. So even though these numbers have, like, an infinite number of digits, there's still a finite process that can generate them.
Right. And that brings us to another really cool thing that Turing figured out. He realized that even though there are an infinite number of them, computable numbers can be systematically listed. You can give them each a unique number, like giving them all ID cards.
Hold on, how is that possible? If there are infinitely many of these computable numbers, how could you ever put them in a list?
Well, think of it this way. Every computable number has a Turing machine that can calculate it. And every Turing machine can be described by a set of rules. So basically, you can give each machine a unique number based on its, description. So by numbering the machines, you indirectly number the computable numbers they can generate.
Okay, so you're essentially saying that there's this one-to-one relationship between Turing machines and computable numbers. So you can use the machines as a proxy for numbering the numbers.
That's it.
Pretty clever.
Turing was brilliant.
Okay, so we've got this idea of the Turing machine. It helps us understand what numbers are computable. But I keep hearing about this other thing, the universal Turing machine.
Oh, yeah. This is where things get really interesting. This is where Turing takes his ideas to a whole new level.
Okay, so what is this universal Turing machine all about?
So imagine a single Turing machine that can simulate any other Turing machine. You just give it the description of another machine, and it acts exactly like that machine.
Wow, so it's like instead of needing a separate machine for each calculation, you have one machine that can do it all.
Exactly. As long as you give it the right instructions, it can do anything.
And this is basically the blueprint for the modern computer.
It is. The idea that we could have a single device that can run any program we give it.
Yeah.
It's all thanks to Turing. And remember, he came up with this in 1936, way before the first electronic computers were even built.
It really is mind-blowing. It's like he saw the future of computing.
He did. And it wasn't just about the technology itself. It was about laying the groundwork for how we think about information processing and how we solve problems in general. It's about breaking things down into simple steps that a machine can execute.
I'm starting to get a little bit of a headache, but it's a good headache.
Right.
So this universal Turing machine, it's powerful, but I have a feeling there are still limits to what it can do. I mean, Turing himself talked about these limits of computability, right?
You're right. Even with all this power, there is still boundaries. Yeah. There's some things that just can't be computed, even in theory.
Okay, this is where I start to feel like my brain might melt. How can there be a number that even a universal Turing machine can't compute?
Yeah, it's a tough one to wrap your head around, but Turing proved it using something called diagonalization. It's a little tricky to explain. Maybe we can dig into that a little more in the next part.
Yeah, maybe let's save the diagonalization deep dive for part 2, because I need a minute to process this. There are numbers out there that, like, no machine can ever compute.
It's wild, right? It's like there's this whole secret universe of numbers that are completely off limits to us.
It's a pretty humbling thought, isn't it? Even with all our technology, there are some things we may never be able to crack.
Yeah, definitely.
Okay, so we've got these computable numbers, Turing machines, the universal Turing machine, and now this idea that there are limits to what's computable. But I want to get back to something I saw in the title of Turing's paper, Entscheidungsproblem. I'll admit I have absolutely no idea what that means.
Ah, yes. The Entscheidungsproblem. That's German for decision problem. It was a major challenge in the world of math and logic back then. Right. Basically, it asked, is there a general algorithm that can tell us whether or not any given mathematical statement is provable?
So like a universal truth checker for math, that'd be pretty handy.
Right. I mean, mathematicians would be ecstatic. Yeah. Just imagine being able to plug any math statement into this algorithm.
Yeah.
And it just spits out yes or no on whether it's true.
Unfortunately, Turing proved that such an algorithm can't exist.
You're kidding. So there are some mathematical truths that we just can't definitively prove or disprove.
That's right. And what's really interesting is that Turing's proof doesn't rely on finding a specific math statement that's undecidable. It's a deeper statement about the limitations of any formal system of logic. Basically, he's saying that there are always going to be true statements that we just can't prove within the system.
Whoa, okay, that's a pretty profound idea.
It is.
I think we've stumbled into some very deep philosophical territory here. Turing's work wasn't just about math and machines. It was about pushing the boundaries of knowledge itself.
All right, I think we need to take a break to let all this information sink in before we move on.
Good idea. Take a moment to digest, everyone. We've covered a lot of ground, but we're just getting started. In part 2, we'll explore how Turing proves those limits of computability and what the Entscheidungsproblem really means for the world of computing. Stay tuned.
Okay, welcome back. I hope everyone had a minute to kind of process all those mind-bending ideas we were talking about.
Yeah, give your brains a rest. It's not every day you encounter ideas that, completely reshape your understanding of what's possible.
Right. It's a lot to take in. So before the break, we were talking about how there are numbers that even a universal Turing machine can't compute. And I have to say, I'm still kind of struggling with that. How can a number be uncomputable?
Yeah, it is a wild thought. But Turing proved it. And his argument is actually pretty clever. You just got to do some mental gymnastics to get there.
Okay.
Do you remember that diagonalization thing I mentioned?
Vaguely. It sounded a bit intense, if I'm being honest.
It is a little intense, but I think we can explain it. Imagine a giant grid, like a spreadsheet, but with infinite rows and columns. Each row represents a different Turing machine, and each column is a different number.
Okay, I'm picturing this infinite spreadsheet, and I'm already feeling a little dizzy.
And if a Turing machine can compute that number, you put a yes in the corresponding cell. If it can't, you put a no.
Right, so we've got this massive grid of yeses and nos mapping out what each machine can compute.
Now, here's the really clever part. Turing figured out a way to construct a new number. Let's call it the diagonal number. And he does it by looking at the diagonal of this grid.
Okay, I'm following so far.
So starting at the top left corner, you move diagonally down the grid. For each cell on the diagonal, if it says yes, you make the corresponding digit in your new number a no. And if the cell says no, you make the digit a yes.
So you're basically creating a number that's like deliberately designed to be different from all the other numbers on the grid.
Exactly. You're building a rebel number. And here's the kicker. This diagonal number can't be computed by any of the Turing machines on the list because, by definition, it's different from each of them in at least one digit.
Oh, wow, I see. It's like a chameleon that keeps changing its colors to be different from everything around it.
Yeah. And that's how Turing proved that there are some numbers that are fundamentally outside of the realm of what any Turing machine, and therefore any computer, can produce.
So it's not just that we haven't figured out how to compute these numbers yet, it's that it's literally impossible to compute them. Wow.
That's right. And it gets even wilder when you start thinking about the implications for what problems can be solved. It means that there are limits to what we can know, even with, like, theoretically perfect computers.
Yeah, it's like there's this whole other dimension of reality that we can't even access through computation.
Which brings us back to that Entscheidungsproblem. Remember that?
Yeah, the decision problem, right?
The idea that there's no universal algorithm to tell us if a mathematical statement is true or false.
Right, right. Are these two ideas, like, connected somehow?
They absolutely are. In fact, Turing's proof that the Entscheidungsproblem is unsolvable. It's directly related to his discovery of these uncomputable numbers.
How so?
Well, think about it. If you had a universal truth checker for math, you could use it to compute any number. You just ask, is this specific decimal expansion equal to this number?
Oh, I see. So if you could solve the Entscheidungsproblem, you could basically sidestep the whole issue of uncomputable numbers.
You got it. But since we know those uncomputable numbers exist, that means there can't be a universal truth checker for math.
It's like this domino effect, one mind-blowing discovery leading to another.
It is, isn't it? It really shakes the foundations of what we thought was possible with math and logic.
I mean, this is heavy stuff. It's like realizing the universe isn't just vast and mysterious. It's also got these regions that are fundamentally inaccessible to us.
That's a great way to put it. But before we get too lost in the existential dread, let's think about what this all means for, regular people.
Right. Why should someone who's not a mathematician or a computer scientist care about these uncomputable numbers?
Well, it's easy to get lost in the kind of abstractness of it all. But Turing's work has these very real, practical implications for everyone. For one thing, it's a good reminder that even with all of our amazing technology, there are still things that we might never be able to figure out.
So it's a reality check on our technological optimism.
Exactly. But it's not all doom and gloom. Understanding these limits also helps us focus our efforts on problems that actually are solvable.
So it's like knowing where the boundaries are on a map can actually make you a better explorer.
Right. And even though we can't compute everything, the things we can compute have already, transformed the world.
Yeah, I mean, Turing's work paved the way for everything from smartphones to the algorithms that, recommend what we should watch next. It's pretty amazing to think about. So we've explored these uncomputable numbers, connected them to the Entscheidungsproblem, and even touched on how it all relates to the real world. I'm feeling a little overwhelmed, but in a good way.
Me too. But I think we should take a moment to reflect on what all of this means for us as humans.
Ooh, that sounds like a perfect topic for part 3, where we dive into the philosophical depths of Turing's legacy.
Sounds good to me. We'll see you there.
All right, welcome back to our final deep dive into the mind of Alan Turing. We've covered a lot of ground computable numbers, uncomputable numbers, Turing machines, the limits of computation. It's been, it's been pretty intense.
It really has. And now as we reach the kind of summit of this mountain of knowledge, we're left with some pretty big questions.
Yeah, and they're not just about math and machines anymore. Turing's work really pushes us to think about what we know and what we can ever hope to know.
Yeah, exactly. So let's take a minute to, appreciate the view from up here. Let's talk about some of the big philosophical ideas that Turing's work has sort of unleashed on the world.
Sounds good to me.
So one of the things that I find most fascinating about Turing's legacy is how it blurs the line between, the mechanical and the human.
Right.
He showed that even a machine, something that just follows rules, can achieve this incredible complexity.
Yeah.
Can even mimic certain aspects of human thought.
It's like he opened up this whole new way of thinking about intelligence.
Right. It's not just about having a physical brain.
Yeah.
It's about the ability to process information, to solve problems.
And that leads to some pretty big questions about what it actually means to be intelligent. I mean, can a machine be considered intelligent if it can, do things that we normally think of as human thought?
Right. And what are the essential ingredients of intelligence? Can those ingredients be, replicated in a non-biological system?
I mean, these are questions that, philosophers and computer scientists are still arguing about today.
They are.
And with AI becoming more and more powerful, we're starting to see machines that can learn, adapt. They can even be creative in ways that, not long ago we thought were exclusively human.
It's an exciting time, but it's also maybe a little bit unnerving. I mean, we're creating these machines that are becoming more and more like us.
Yeah, and that's where I think Turing's insights about the limits of computation become even more important. Even with all the advances in AI, there are still those fundamental constraints. There are going to be problems that even the most sophisticated AI can't solve.
Right. It's a good reminder that we can't just assume technology can solve all our problems.
So it's a matter of balancing this kind of excitement about the possibilities of AI with a healthy dose of, well, realism about its limits.
I think that's a great way to put it. And Turing's work, I think, offers us this really valuable perspective.
How so?
Well, he showed us that even within those limits, there's still this incredible potential for, discovery and innovation.
We can still use computation to understand the world better, to solve complex problems, and even to create new forms of art and expression.
It's like we can't explore every corner of the universe, but the parts we can explore are still incredibly vast and amazing.
And speaking of exploring, one of the most profound things about Turing's work is how it's expanded our understanding of the universe itself.
Oh, absolutely. His ideas about computation have become essential tools for scientists in, practically every field.
It's like Turing gave us a new language for understanding the universe, a language based on algorithms and information processing.
It's a powerful language, and it's allowing us to make discoveries that were, completely unimaginable just a few decades ago.
As we've been talking, I keep thinking about what Turing himself would think about the world we live in today. A world where his ideas are now so deeply woven into our technology, our culture, even our understanding of what it means to be human.
That's a great question. I imagine he'd be, pretty amazed,
Right.
thrilled to see how his ideas have, blossomed and led to so many breakthroughs, but probably also a little bit cautious.
Oh, yeah, definitely. He was very aware of the ethical implications of technology, and I think he'd probably urge us to use these powerful tools responsibly.
I agree. And that brings us to another really important aspect of Turing's legacy, the need for, inclusivity and diversity in computing.
Yeah, I mean, he himself faced a lot of discrimination and persecution because of his sexuality.
Right. And his story is a reminder that we need to make sure that everyone has the opportunity to contribute to the field,
Hmm.
regardless of their background, their identity, their beliefs.
That's how we'll continue to push the boundaries of what's possible and create a future that benefits everyone.
Absolutely.
Well, I think it's safe to say that our listeners are now fully equipped to continue their own exploration of Turing's world. We've given them the map, the compass, and most importantly, I think, the curiosity to keep asking questions.
And who knows, maybe one of our listeners will make their own contribution to Turing's legacy. Maybe they'll make a discovery that changes the world.
Wouldn't that be amazing?
It would.
That's a great thought to end on. Thanks for joining us on this deep dive into the incredible mind of Alan Turing. Until next time, keep exploring, keep questioning, and keep computing.